Let's talk about an orthonormal set of functions. Let's say you have a set of functions, f1, f2, f3, and so on. We say it's an orthonormal set, okay? If each function is normalized, what does it mean when each function is normalized? Like if I were to ask you, what is the integral of f1 star f1 d tau if f1 is normalized? Equal to 1. That's what it means. What's the integral of f5 star f5 d tau? Oops. f5 star f5 d tau. 1. That's what normalized means, right? Then we can say the function is also, we say it's orthonormal if each function is orthogonal to all the other functions in that set. Okay, what does orthogonal mean? Orthogonal means, like if I took a pair of functions, f1 star f2, okay, d tau, if I did that integral, then that is equal to 0 if f1 and f2 are orthogonal. Okay, so that's what orthogonal means. The integral of the first function star times the second function over all space is equal to 0 if the two functions are orthogonal. Okay, so the whole set, we say, is orthonormal if the functions in the set obey these conditions. Each one is normalized, each one is orthogonal to all the others. We can summarize all of this by saying this one right here. Okay, integral of f sub I, and I and j can be any number, 1, 2, 3, 4, right there, any index right there. Okay, so you say integral of f sub I star fj d tau must be equal to 0 if I is not the same as j, okay, or 1 if I and j are the same. Okay, and this expression right here has a special symbol. You call that the delta ij. Okay, this is known as the Kronecker delta. So that symbol delta sub ij means that's equal to 0 if I is not equal to j, that's equal to 1 if I is equal to j. You can also abbreviate that simply using with Dirac bracket notation. This one right here is just f sub I in the bra, f sub j in the kit. Okay? The function that starred goes in the bra, and then the other function goes in the kit. Or if you're really lazy, you can just say I, j. If you know what function you're referring to, you already know what the functions are, then you can just say that's another abbreviation. So you see 3 different ways of abbreviating that integral right there, provided you know what those functions are. Okay? All right, so let's just do a quick check. Let's say functions f1, f2, and so on is an orthonormal set. Which of these is equal to 0? Okay, that means integral of f1 star f2 d tau is 0. Okay, what about this one? That's equal to 1. That's I equal to j, right? So that's integral of f3 star f3 d tau. That's equal to 1. So that's a normalized function. F3 is a normalized function. F1 and F2 we say are orthogonal to each other. Okay, that's the expression you use. You say function F1 and function F2 are orthogonal to each other. Okay, which of these is correct? The first one or the second one? Which one? Huh? The first one's correct. F4 star F5. So if it's an orthonormal set, okay, if you have 2 different functions in your integral, then your integral is 0. How about the second one? That should be equal to 0. We say F7 and F5 are orthogonal to each other. Okay. Let's define what a complete orthonormal set is. Okay? So if we have a set of functions, we say that set is a complete orthonormal set if, okay, any function that obeys the same boundary conditions is equal to a linear combination of the functions in the set. Okay? So what do we mean by obeying the same boundary conditions? Let's say you have a set of functions, okay? Let's say all your functions go to 0 when x equals, let's say, x equals 2. And you should plot up your function. Oops. Okay, let's see. So let's say when x equals 2, this for example, okay? Let's say all your functions go to 0. So this might be f1, this might be f2, f3 might go this way. And they all obey the same boundary conditions. Okay? And maybe some other condition over here. Oops. Another part here, they all go to 0 there as well. So those are what you call boundary conditions. Okay? So if you have a function that follows the same boundary conditions as your orthonormal set, okay, so let's say g, okay, let's say function g obeys the same boundary conditions, then you should be able to write g as c1 f1 plus c2 f2 plus c3 f3 and so on. What do you call that? Constant times function 1 plus constant times function 2 plus constant times function 3. You call that a linear combination of functions f1, f2, and f3, right? So this is a linear combination of f1, f2, f3, and so on. So any function, any other function, okay, that may not be in that set, that may not be part of that orthonormal set, but if that function obeys the same boundary conditions as the functions in the set, you can write it as a linear combination of the functions in the set. So, and you can in fact show that the coefficients is equal to that, and the integral of g star g d tau is just the sum of the squares of the coefficients. Let's show that. Okay. Let me see if I did that elsewhere. Okay. So let's just make it. Let's make it simple. Let's say g. Okay. So g is. Let's take this integral right here. Okay. What is the integral of f? Let's make it simple. Let's say f3 star g. What would that be? D tau. Just for example. Then it's going to be what? Integral of f star. What is g? c1 f1 plus c2 f2 plus c3 f3 plus and so on. D tau, right? Okay. And what would that be equal to? Integral of f1, f3, right? f3 star c1 f1 d tau, right? Plus integral of f3 star, so I just distribute, right? f3 star c2 f2 d tau plus integral of f3 star c3 f3 d tau plus something else, right? Or in bracket notation, I can say this is f3 c1 f1, right? Plus this is going to be f3 c2 f2. And this is going to be f3 c3 f3, right? So what can I do at this point? What can I do with my constants in my integral? This one. I can pull that out of my integral, right? So this will just give me c1 f3 f1, right? Plus c2 f3 f2 plus c3 f3 f3 plus and so on and so forth. Right? Well, what happens now? What is f3 f1? 0. Why? They are, what's the word? Orthogonal. Okay? F3 and F1 are orthogonal to each other. What is F3, F2? Also 0, they are orthogonal to each other. What is F3, F3? This is 1 because we say F3 is normalized. Each and every function in your set is normalized, right? So what do you think these extra additional terms are going to be? 0, because F3, we say, is orthogonal to all the other functions. So what's the only constant that's left? C3. So we've shown that C3 is equal to F3 star G d tau. Okay? In general, C sub I would be integral of F sub I star G d tau. And that's what we're saying right here. Okay? This one right here. Now, can you show this one? Let me get you started, and that will be homework number 3 for today. Okay, this one right here says what? Integral of C1 F1 plus C2 F2 plus and so on and so forth, right? Time a star, right? So that's your G, and the other G, and there's a star there, and the other G is also C1 F1 plus C2 F2 plus so on and so forth, d tau. Okay? So you can just to make things easy for you, let's just use 2 terms. Okay? If you use 2 terms, I want you to show for your homework that this is in fact equal to absolute value of C1 squared plus absolute value of C2 squared plus absolute value of C3 squared and so on. Okay, absolute value of C3 squared and so on. But if you only use 2 terms, then you only get C1 squared and C2 squared. So that's what this means right here, summation of C sub I squared. Okay, so that should be an easy proof. All you have to do is FOIL it, right? So this one, okay, this one, and now you just do the first 2 for each one. So I'll give me 4 terms. Okay, huh? I'm sorry. You just expand all of this, and then you should get C1 squared plus C2 squared. And then this is going to be, if we leave out, all right. So let's apply what we just learned. Suppose F1, F2, and so on is an orthonormal set, and G obeys the same boundary conditions, and G happens to be equal to 2F1 plus 3F2. What is this integral equal to? F2 star G is C2. What is C2? 3. Okay? Let's try this one. Let's say F1, F2, and so on forms an orthonormal set. If G obeys the same boundary condition and happens to be equal to 2F1 plus 3F2, what is this integral equal to? So integral of G star G d tau is equal to C1 squared plus C2 squared plus C3 squared plus and so on. What is C1? C1 is 2 squared. C2 is 3, it's absolute value of 3 squared. And C3 is what? 0. What is C4? 0. Everything else is 0, right? So that gives you 4 plus 9. That's 13. So is G normalized? No. How do I normalize G? So how do we solve this? You're going to say then that absolute value of 2n squared plus absolute value of 3n squared must be equal to 1 if G is normalized, right? So what is n? So 4 times absolute value of n squared plus 9 times absolute value of n squared is equal to 1. Okay. So n squared times 13 is equal to 1. Absolute value of n squared is 1 over 13. Absolute value of n is 1 over square root of 13. Okay?